So welcome back to this video. So we're defining real n space, and I've said it's going to be an n-dimensional real vector space with Euclidean norm. So we've discussed the n-dimensional real vector space part. We now need to discuss the concept of the Euclidean norm. So the aim of this is to get a notion of the size of a vector in your vector space, or a notion of the length of a vector in your vector space. In the real line, you have a notion of the size or the length of a real number, which is the modulus function, the absolute value function. We need a corresponding notion for our vector spaces. So a norm is the fancy mathematical name for a size function put on a vector space. So we're going to put a norm on our real vector spaces in order to turn them into real n spaces. Now there are multiple different norms that you could put on your real vector spaces. We're going to put a specific one, the most intuitively obvious one to use, which is called the Euclidean norm, and this is it written here. So it is a size function, and this is the notation for it. So the norm of a vector x is written like so, similar to the symbol for absolute value of a real number, but now instead of just having single lines on either side, we have double lines on either side of our symbol that's representing a vector rather than a real number now. And it is a function, so this is how we write that it's a function. Here is the norm symbol, and then we don't put a specific vector in there anymore, so we put a dot there, and it's a function from our n-dimensional real vector space into the real numbers. So it's going to map each vector onto a real number, and that real number is going to be the norm of that vector, the size of that vector. Now, more normally, the way we'd write that is like so. We take our vector x and we put the two lines on either side of it, and this is the norm of x, and this is how we're going to define the Euclidean norm for our n-dimensional real vector space. It's going to be the square root of the sum from I is equal to 1 to n of xi squared, where the xi's are the components of your n-dimensional vector x. So x is equal to this vector x1, x2, all the way up to xn. So these are all real numbers here, so you can square them. You'll then end up with a non-negative real number. You can add them all together. You'll again end up with a non-negative real number, and then as you've got a non-negative real number, you'll be able to square it to get another non-negative real number, and that will be the norm of your vector. So I've written this Euclidean norm out for the n is equal to 2 case, and I want to show you how it corresponds to an intuitive notion in the 2D plane. So the norm of our vector x in R2 is going to be equal to the square root of, and then this sum written out explicitly for n is equal to 2 is just x1 squared, the first component squared, plus x2 squared, the second component squared. And then if we think about our vector having a point in the two-dimensional plane, let's have it here, so this is our vector x1, x2, then what we can do is draw our arrow going from the origin, our straight line arrow going from the origin to our point, and then this concept of the norm that I've defined on my R2 vector space, this you can see corresponds to the Pythagorean length of this arrow here, because that's arrow's length will be the side x1 here squared plus this side of the right angled triangle x2 squared, and then square root that, and you'll get the length of the hypotenuse here. Similarly, in R3, the norm will correspond to the Pythagorean length of your arrow for your vector. So the norm of our vector x is going to be the square root of x1 squared plus x2 squared plus x3 squared. If you then imagine your vector x1, x2, x3 in the three-dimensional space, and you draw an arrow, a straight line arrow, from the origin to your point, the length of that arrow will be given by the norm here. So this Euclidean norm, in the case of R2 and R3, is capturing the normal Pythagorean length of the arrow in the two-dimensional and three-dimensional spaces. But of course, this mathematical definition of the norm can be extended into the higher dimensional real vector spaces, so we can therefore have this norm on our n-dimensional real vector space, and with it, we will call that a normed n-dimensional real vector space, and that's what real n space is going to be for our study of analysis going forward. So now what I want to devote the rest of the video to is showing you three properties of this Euclidean norm that we've defined on our real vector space that are utterly essential for it to obey in order for it to earn the title of being called a norm. So the first one is that it is a positive definite function. So one, this means that any vector is always mapped onto something that is greater than or equal to 0 by this norm function. And you can see that that's the case just looking at the definition. So the norm of our vector x is going to be the square root of the sum from I is equal to 1 to n of the xi squareds. The square root is always going to be a non-negative is always going to give a non-negative output. Think of the square root function. When it's applied to any non-negative real number, the output is always non-negative. So certainly it's going to be always greater than or equal to 0. But in addition, positive definite means more than that. It doesn't just mean that it spits out something that's non-negative. That would be just non-negativity. Positive definite means that the only time when it's equal to 0 is in the trivial case. And the trivial case is when x is the 0 vector. So the only situation where the norm of x is equal to 0 is when x is equal to the 0 vector. And you can see that again looking at the definition. When x is the 0 vector, then all of the components are 0. So you're taking 0 squared, adding it together n times, you'll end up with 0, and when you square root 0, you still end up with 0. So yes, x being the 0 vector implies that the norm is 0, but also it works the other way around. When the norm is 0, you can conclude that your vector is the 0 vector, because the moment one of the components is non-zero, meaning that your vector isn't the 0 vector, then when you square it, again, you'll end up with something that's positive. You won't end up with something that's 0. Nothing except 0 squares to give 0. So then when you take the sum, you'll still have something that's positive, because everything that you're adding together is non-negative, so you're not going to be able to cancel that positive thing that you've got out. So you'll be taking the square root then of a positive number, and the square root of a positive number is a positive number. The only thing whose square root is 0 is 0 itself. So yes, if you don't start off with the 0 vector, you're not going to end up with a norm that's equal to 0. So the only thing that has a norm equal to 0 is the 0 vector. And that's what positive definite means. It means 1, that it's non-negative, and 2, that the only time that it's equal to 0 is in the trivial case. Everywhere else it's positive. The second property that it obeys is that it behaves nicely with scalar multiplication. In particular, if you take the norm of lambda, which is a scalar, so a real number, times your vector x, this is equal to the norm of the vector x times the absolute value of your real number, your scalar, lambda. So proving this is pretty easy, so we'll start with the left-hand side and we'll get to the right-hand side. So if we consider lambda times our vector x, so we're doing this in arbitrary dimensions, so our vector is x1, x2 all the way up to xn. Our vector lambda times x is lambda x1, lambda x2, all the way up to lambda xn. The norm of that, Euclidean norm, is then the square root of the sum from I is equal to 1 to n, and then we're going to have lambda xi squared, which of course is lambda squared, times xi squared. And you'll notice that lambda is something that we're going to be able to pull out of this sum because it's common to every single one of the things that we're summing up, or lambda squared even is common to every single one of the things that we're summing up. So next step, pull that lambda squared out. So this is equal to the square root of lambda squared times the sum from I is equal to 1 to n of xi squared. And then, of course, we can pull the lambda squared out of the square root, or we can split it into the square root of lambda squared times the square root of the sum from I is equal to 1 to n of xi squared. And then, of course, the square root of lambda squared is the modulus of lambda. Remember, it's not actually just lambda back again, because if lambda started off as a negative number, when you square it you end up with a positive number, and when you take the square root of it you end up with the positive version of the original lambda, so you end up with the absolute value of lambda, not lambda back again. So this is equal to then the absolute value of lambda times the square root of the sum from I is equal to 1 to n of xi squared, but of course that is the norm of the original vector x. So we've proven then that the norm of lambda x is equal to the absolute value of lambda times the norm of x. So indeed, scalar multiplication does play nicely with our Euclidean norm on n-dimensional real vector space. The third and final property is the most difficult and is the triangle inequality, and it says that the norm of the sum of two vectors, so x plus y, is less than or equal to the norm of the vector x plus the norm of the vector y. So to show you intuitively what this means and why it's called the triangle inequality, think of the R2 case and the corresponding concepts in the 2D plane. So if we have a vector x, and this is the arrow going from the origin to that point x, and then let's say that we have a vector y, and then here is the same arrow that would go from the origin to that point y, so the point y might be here, and then we're adding the vector x to the vector y, then the corresponding notion in the 2D plane is putting the arrows like this, and then we're going to get this resultant arrow here, which will be the vector x plus y, will correspond to the vector x plus y. And then I'm saying, look at the length of this vector x plus y, and it's going to be less than or equal to the length of the vector x and the length plus the length of the vector y. So it's effectively saying that this side of the triangle is always less than or equal to the two other sides of the triangle added together. And you'll have equality when these two arrows were pointing in the same direction. So if you can imagine now that the point y maybe was here, then that y vector would point in the same direction as the x vector. So when you added them together, it would be like this, and you can see that the resultant vector you get would have length just equal to the length of the vector x plus the length of the vector y. So that's just some intuition from R2 as to what the triangle inequality means and why it's called that. What we now need to do is prove this for an arbitrary n-dimensional real vector space with this Euclidean norm, and to do this we're going to use the Cauchy-Schwarz inequality. So I've just written out our two vectors x and y in full. So here's our x vector, x1, x2, all the way up to xn. Here's our y vector, y1, y2, all the way up to yn. Again, I'll remind you we're doing this for arbitrary n. And then these two vectors will always obey the Cauchy-Schwarz inequality. We did a video on the Cauchy-Schwarz inequality earlier in this playlist. So it says that the sum from I is equal to 1 to n of xi, yi squared is always going to be less than or equal to the sum from I is equal to 1 to n of xi squared times the sum from I is equal to 1 to n of the yi squareds. So we're going to tinker with this inequality and eventually turn it into the triangle inequality for the Euclidean norm. So firstly note that these things that we've got over here are related to norms. Indeed, this is the norm of the x vector squared, and this is the norm of the y vector squared. So the first thing that I'm actually going to do is take the square root of both sides of this inequality, and taking the square root doesn't change the inequality because of the fact that the square root function is a strictly increasing function. So if the input on this side is less than or equal to the input on this side, then the output that we're going to get on this side is still going to be less than or equal to the output from this side. So let's take the square root of both sides and we still have the same inequality less than or equal to here. So when you take the square root of this, you don't get back sum from I is equal to 1 to n of xi, yi. You get the absolute value of that, because this thing could have been negative, then when you square it, it will become positive, and when you take the square root, you'll get the positive version of this. So you get the absolute value of the sum from I is equal to 1 to n of xi, yi xi, yi. Is less than or equal to, and then the square root of this side, that will then be the square root of this times the square root of this, which is the norm of the x vector times the norm of the y vector. Now my next move is going to be to get rid of those absolute value signs there. So if this thing is positive, then the absolute value is still the same, and I know that it's less than or equal to this. If this is negative, then if the positive version is less than or equal to this, then the negative version is definitely still less than or equal to this. So I can get rid of the absolute value signs, and this inequality is still going to hold true. So sum from I is equal to 1 to n of xi times yi is less than or equal to the norm of x times the norm of y. Next move is very simple. I'm just going to multiply by 2. No harm in that. Next, what I'm going to do is I'm going to add the same thing onto both sides of the inequality. So I'm going to add the square of the norm of the x vector, and I'm also going to add the square of the norm of the y vector. So that's the right-hand side part, and then I've also done the same thing on the left-hand side. So I've added the square of the norm of the x vector and the square of the norm of the y vector. So you might not necessarily know why am I doing this. It's all aiming to turn this into this. So you'll see I have constructed this so that it's going to work. We're going to end up turning the Cauchy-Schwarz inequality into our triangle inequality for the Euclidean norm. Trust me, it doesn't take too many more steps. So now what I'm going to do is I'm going to cleverly rewrite both sides. So let's start with the right-hand side because it's simpler. So notice that what I've got here now factorizes quite nicely, and it factorizes into this, the norm of x plus the norm of y squared. So if you expanded this, you get the norm of x squared, which is this, you get the norm of y squared, which is this, and then you get the cross terms, which is 2 times the norm of x times the norm of y. So indeed, this is equal to the right-hand side. Then I've rewritten the left-hand side in a slightly more complicated way. I have written out what the square of the norm of the vector x and the norm of the vector y actually are. So this is the sum from I is equal to 1 to n of xi squared, and this is the sum from I is equal to 1 to n of yi squared. And then I've combined all of these three together in one sum. So it's the sum from I is equal to 1 to n of xi squared, which is this bit, plus 2xiyi, which is this bit, plus yi squared, which comes from this bit. So next step, no manipulation to the right-hand side, it stayed exactly the same, and then a simpler manipulation to the left-hand side. We're just going to factorize this thing here. So this can be factorized as xi plus yi squared. If you expand this, you'll get xi squared plus the cross term, which is 2xiyi plus yi squared. So sum from I is equal to 1 to n of xi plus yi squared is less than or equal to this thing. And now the final brilliant step. So this thing that we've got on the left-hand side, this is just the Euclidean norm of x plus y squared. So we can turn this left-hand side into the norm of the x plus y vector squared, because if you think about what this norm would be, the vector x plus y, you need to add all of the components of the x vector component-wise to the components of the y vector, and then if you wanted to take its norm, you'd need the square root, but we're taking the norm squared, so we can abandon the square root sign. So we just have sum from I is equal to 1 to n, and then we'd have x1 plus y1 squared plus x2 plus y2 squared plus all the way up to xn plus yn squared, and that's what we've got here. So sum from I is equal to 1 to n, xi plus yi squared. This is indeed the norm of x plus y squared. But now all we need to do is take the square root of both sides of this inequality. I've already argued for why that doesn't affect the inequality. We don't need to worry about having absolute values of these things because these are all going to be positive. So we can now conclude that the norm of x plus y is less than or equal to the norm of x plus the norm of y. So that is how you go from the Cauchy-Schwarz inequality to showing that the triangle inequality for the Euclidean norm holds true for any arbitrary n-dimensional real vector space. So that concludes then the three major properties that our Euclidean norm obeys: positive definiteness, behaving nicely with scalar multiplication, and the triangle inequality. And these three properties are actually the defining three properties of any norm on any vector space. They always have to obey these three properties in order to qualify for being called a norm. So basically we've just proven that the Euclidean norm is indeed a norm. Now, we're about to finish, but before we do, let me just say that the reason that equipping the n-dimensional real vector space with a Euclidean norm is so important so that we can do analysis is because it gives us a notion of closeness of the vectors, which is really important in analysis. So in particular, if you have 2 points in your vector space, and we'll just use the picture of our 2D plane corresponding to our 2D real vector space. So if we have these 2 points, let's call this one x and this one y, then if we look at the vector x minus y, that will be this little arrow going from y to x, and then if we look at the norm now of that vector, that will give us a notion of how close the point x and the point y in our vector space are. So that's why this norm is so important. We're going to use it as our notion of closeness in our real n space. So we'll leave it there. Thank you for watching.